In circular motion, an object travels on a circular path with center of the circle at O and radius of curvature, r. The angle of rotation, theta, is the angular analog of distance in linear motion. The arc length, s, after the Latin word spatium, equals r times theta. When theta goes around a full circle, which is 2 pi in radians, the arc, s, equals 2 pi r. And that's the circumference of a circle, as you recall from geometry. Make sense? With theta being the angular analog of distance in linear motion, angular velocity, omega, is the angular analog of velocity, v, and angular acceleration, alpha, is that of acceleration, a. Consequently, we have the angular motion equations describing omega and theta, just like we do with v and d in linear motion. It should be noted that the direction of angular velocity omega is along the axis of rotation. An easy way to remember is by using the right-hand rule. Wrap your right hand around axis of rotation with fingers pointing in the direction of rotation. The thumb would be pointing in the direction of angular velocity, omega. Similarly for angular acceleration, wrap your right hand around axis of rotation with fingers pointing in the direction of increasing rotation rate. The thumb would be pointing in the direction of angular acceleration, alpha. Tangential velocity, v, is the instantaneous linear velocity of an object in circular motion, and is always at a tangent to the circular path. The magnitude of tangential velocity is the change of arc length within a time interval, delta t. Since the arc length is the radius times theta, tangential velocity is thus the radius times the changing rate of theta, which is the angular velocity, omega. The direction of the change of tangential velocity in uniform circular motion is pointing to the center of rotation. This can be illustrated by the velocity vector diagram here. When the arc length becomes infinitely small, delta v will become obvious pointing to the center of rotation O. This change in tangential velocity results in a center-pointing acceleration known as the centripetal acceleration, a sub c. The magnitude of the centripetal acceleration can be derived based on the triangle formed by the velocity vector and the one by radii OAB being similar. For similar triangles, we have the ratios of the sides being equal, or delta v over v equals delta r over r. When the change in theta is infinitely small, the arc length equals the change in radius, or delta s equals delta r. The magnitude of centripetal acceleration equals delta v over delta t, which is v squared over r. It is often useful to have a relationship established between centripetal acceleration and angular velocity. Since we have v equals r times omega, a sub c thus equals r times omega squared. The centripetal force, based on Newton's second law of motion, equals mass times the centripetal acceleration. Therefore, F sub c equals m times v squared over r. And in angular velocity terms, it equals m times r, times omega squared. It is critically important not to confuse tangential velocity with angular velocity. Both terms are associated with circular motion, but tangential velocity is actually a linear velocity at a tangent to the circular path. It is equally important not to confuse centripetal acceleration with angular acceleration. Both terms again are associated with circular motion, and centripetal acceleration is resulted from direction change of tangential velocity, while angular acceleration is from change of angular velocity. Suppose we are constructing a spaceship with the crew quarters rotating to create an artificial gravity similar to the Earth gravity of 9.8 meters per second squared. For comfort of the crew members, we set rotational velocity to 1 rpm, which comes to approximately 0.1047 radians per second. When rpm is too high, one can experience discomfort such as dizziness like some of us do when riding the Mad Tea Party ride at Disney. For crew members to experience artificial gravity, the centripetal acceleration needs to match Earth gravity. This is because an object in circular motion wants to maintain its inertia of staying in the tangential path, and feels the gravity as the circular motion pulls it away from the tangential path. We now look at the centripetal acceleration, a sub c equals r times omega squared. With A, sub c, and omega set, the rotating quarters need to have a radius r of 893.65 meters, which is almost 2 kilometers in diameter, a quite sizable ship. If we are to reduce the radius of rotation, we must increase the angular velocity. 1 rpm is a rate most people feel comfortable with. For some people, especially after training, 4 rpm can be an acceptable rate. Because the centripetal acceleration is proportional to the square of angular velocity, a 4x increase in omega allows a 16x reduction in r, which comes to 55.85 meters, about 110 meters in diameter, the size of a football field. It's still quite large, but certainly more manageable than the earlier 2 kilometers design. Geostationary orbit is a circular orbit above Earth equator. Satellites in the geostationary orbit have the same angular velocity as Earth's, and thus appear to be stationary to observers on the ground. Communications satellites started using geostationary orbit back in the 1960s. Satellite antennas on Earth do not need to rotate to track them. Geostationary orbit remains a popular orbit today, for weather and GPS usage as well. But, what is the altitude of this geostationary orbit? To answer this question, we use Newton's law of universal gravitation F equals g times mass 1 times mass 2 divided by the square of the distance between the two objects. With F equals ma, the Earth gravity a satellite experiences at an altitude of h equals g times Earth mass m sub e, divided by the square of the sum of Earth radius and the altitude. The centripetal acceleration the satellite experiences is Earth radius plus altitude then times angular velocity squared. Since we know the satellite is going with the same angular velocity as Earth, which is 23 hours, 56 minutes, and 4 seconds to complete a full rotation, we can find the altitude of the geostationary orbit h to be cube root of g m sub e over square of omega, minus Earth radius r sub e, and it comes to approximately 35,785 kilometers. Very good. The third problem we are going to look at is a moving car, trying to avoid colliding with an obstacle. We are comparing two scenarios between simply using the brake and making a uniform circular motion turn without braking. We would like to see which method results in a shorter distance before reaching the obstacle. In both cases, we require no slipping. In other words, we cannot overcome the static friction. For the braking case A, we use the work-energy theorem, which states the net work on a system equals the change in the system's energy. There is no change in potential energy as the car is moving on a flat surface. The initial kinetic energy is 1/2 mv sub 0 squared, and the final kinetic energy is 0 because the car stops. The maximum friction force without slipping is the static friction coefficient times the normal force to the surface, which is the weight of the car, or m times g. The net work done by the friction is negative μ sub sm g times the braking distance d sub max. The negative sign comes from the friction force is always against the motion of an object. Equating the net work with the change in energy, we can obtain d sub max equals 1/2 of v sub 0 squared over μ sub sg. In case B, we are not using the brake, rather we are turning the car in a uniform circular motion such that, with properly selected radius of curvature r, the centripetal force is no greater than the static friction force to avoid any slipping. As you recall, the centripetal force equals m times v sub 0 squared over radius of curvature r, and the static friction force again is μ sub smg, equating the two, d sub max, which is the radius of the turning curvature r, equals v sub 0 squared over μ sub sg. We now know that the braking method requires a shorter distance than the uniform circular turning approach, 50% shorter to be exact. Let's go a little further deeper. Continuing case B, suppose an engineer designs the turning roadway with a banking angle of beta to reduce d sub max with no slipping. The normal force F sub n has a vertical component equaling its weight and a horizontal component contributing to the centripetal acceleration. A second element contributing to the centripetal acceleration is the horizontal component of the friction force. Therefore, we have two equations listed here. Substituting f sub n from equation 1 into equation 2, we have mg over cosine beta times sine beta plus mu sub s times mg over cosine beta times sine beta equals m v sub 0 squared over r. Simplifying the equation a bit, knowing sine over cosine is tangent, we have the d sub max equals v sub 0 squared over the sum of tangent beta and mu sub s times g. Note that, if tangent beta equals mu sub s, d sub max of case B will equal d sub max of case A. Further increase the banking angle beta, case B d sub max can become smaller than case A's. However, it should also be pointed out that this simplified approximation is for small banking angle only. When beta increases significantly, other factors must be taken into consideration. Let's stop here for now. I hope you enjoy this session, and please hit the like button, subscribe, and share. Thank you.